All right, hello to those who are listening to this and watching this in the future, and hello to everyone here again. I'm David, I'm the coordinator of the Maths Learning Centre. It's semester 1, 2021, and this is a revision seminar for Statistical Practice I. I've spent some time asking people what they want me to talk about, and they have asked to talk about the Chi-Squared test and the two different kinds of ANOVA. Okay. All right. Rules are that you, if you're listening to me in the future, like on YouTube or on Echo 360 tomorrow, then you can't do this. But everyone who is here live can interrupt me at any time if I make a maths mistake, if I lose a minus sign or I circle the wrong thing or I spell something wrong. Please interrupt me immediately and let me know. Definitely don't wait for 5 minutes and then tell me I did something wrong. Otherwise, feel free to interrupt me at the end of a sentence and you can ask any questions you like. This is your revision seminar. The purpose is for you to make sense of the stuff in your course. So please ask whatever questions you've got when we get there. Okay. Okay. When I think about statistical tests, I think about the situations that they come from, like the situations that they work on, because every statistical test is designed to answer a specific question in a specific situation. All right. And the situation generally requires you to understand what kind of data is recorded about each individual object or person or thing in your data. And the kinds of information you can write down are called variables in statistics, and variables come in two flavors. They come in either categorical or quantitative. Is that what they call them in this course? Other courses in other places in the world or in other disciplines will call them by different names. You might hear them called qualitative variables. You might hear them called numerical variables. But I think in this course it's categorical and quantitative. Feel free to correct me there. I help people in lots of different disciplines and the words are different for statistics. So there are two kinds of things that you could record about individuals. The Chi-Squared test is specifically designed for situations where you've only recorded categorical variables. So you might have some objects that don't have to be people, they could be houses, they could be petri dishes, they could be rabbits. And these things have two bits of information recorded about them. And these bits of information are have categories recorded about each individual. I'm going to draw them with boxes. That's what those boxes mean. There's categories. Okay, and the purpose of the purpose of the Chi-Squared test is to decide whether being in one of these categories makes a difference to being in one of the other categories. And so in my head, I picture that like this. Something like that. How does being in one of these categories make a difference to being in one of these categories or vice versa? Or does it make no difference which one of these you're in? Does it really not make any difference to which one of these you end up in? The important thing with the Chi-Squared test is that most of the time you are specifically interested in one particular direction. You're interested in one of them affecting the other, but it doesn't really matter. It could go either way. And statistics for any test is not capable of deciding what order things happened in because the data in your computer is just words and numbers. It can't tell that. But it's very important to know that each person is only in one of these categories at a time. or fish or rabbit or house or petri dish or whatever it is that these objects are. It's also true over here. It doesn't. People are only allowed to, or things are only allowed to be in one category at a time. Okay, so that's what chi-squared tests are designed to do. They answer the question of is there a relationship? And in fact, all hypothesis tests pretty much answer that same question of is there a relationship? No matter how it's pitched about whether it's a difference between means or whether it's a difference between categories or whether it's regression or ANOVA, they're all really about whether there's a relationship between variables. And for chi-squared tests, it's a relationship between categorical variables. So for example, you give your friends a meal with chili and a meal without chili. Each person has only one meal. And you ask them whether they feel hot or not. That's my story that I'm telling. This is my classic story. I always use chili as my example because I can only be creative so often. And so that story is that you're wondering, so this is the story, and I haven't said what the actual question is, but the natural question is, does chili make a difference to how hot you feel? Does chili make a difference to whether you feel hot? That's the question I'm asking. Now, that's currently not written as a statistics question, but almost all research doesn't begin as a statistics question. So I have recorded about each person. I have recorded whether they feel hot or not, which is a yes or a no. And I've had whether they had chili or not, which is a yes or a no. And I want to know, does having chili make a difference to whether you feel hot? And I could ask that question. I could say, does being yes for chili make it more likely to feel hot and no for chili less likely to feel hot? That's what I'd be interested in. And so I could be interested in the proportion of people in the chili group that feel hot and the proportion of people in the no group that feel hot, and be wondering whether those two proportions are equal or not. So this could be done with a z-test for two proportions. I don't know if that's in this course anymore, it used to be, but it could also be done with the chi-squared test, because the chi-squared test directly just answers the question of, are these variables related? How are we feeling? Let me know. I'll let you know when I say how you're feeling. Sometimes it's okay to respond with that, to pretend that I meant, do you have any questions? Okay, that's the idea of it. This one was a proper experiment. Well, you know, not a proper experiment by a scientist, but it's an experiment where I did things to people and then I saw whether the category was different afterwards. But you can also do ones where you just happen to find individuals and write down the information you have about them. And in that case, often we don't know which direction the arrow goes, but the statistics can never tell which way the arrow goes anyway, and so that's fine. All right. This is where I'm just going to pause for a moment to just have a look at the notes. So I've just had a question. What is the difference between the z-test for two proportions and the chi-squared test? There are two answers for that. One is that they're not different in the sense that they are trying to answer the same question. It's both the same situation, and everybody's, just a second, different people here. And in fact, they ought to produce pretty much the same p-value. So the z-test for two proportions and the chi-squared test in the situation where there's two categories here and two categories here will produce the same p-value. Possibly a bit off because one of them's an approximation, but they're both approximations in different ways. But roughly, the difference for this one is that the z-test for two proportions can only be used in a situation where there's two categories here and two categories here. Whereas the chi-squared test can be used no matter how many categories there are on either side. So that's one difference. So I'm just going to z-test for two proportions versus the chi-squared test. So they're the same in the sense that if you can do both of them, they'll produce roughly the same p-value. They'll answer the same question and give the same p-value. They're different in that the z, I put crosses on my z's, z-test for two proportions only for the situation where there's two categories being related to two categories. This category causes you to make groups and this category is the outcome. But the chi-squared test for any, so with the chi-squared test you can do, 4 categories here and 3 categories here and it will work fine. So that's one difference. The other difference is that the z-test for two proportions has a confidence interval to go with it. You can turn your calculation for the test statistic into a similar calculation for a confidence interval. But for the chi-squared test, it's not set up to do that. There's no confidence interval. That's the difference. There's one further difference is the z-test for proportions. If you're going to set it up to appease a statistician, you're supposed to directly mention the proportions that are involved, whereas the chi-squared test, you don't mention any proportions, you just say the null hypothesis is that they're independent. So that's the other difference. I'll pop that down too, and I'll talk about those again. It'll be something like H0 is that the proportion in situation 1 is equal to the proportion in situation 2, whereas for the chi-squared test, it'll be H0 is the variables are independent, and you'll say it as words. They're the similarities and differences. One of the reasons I did what I just did there was that it is always a good idea to look at the things in your course and say, how are they similar and how are they different? Because knowing how things are similar and how they're different will help you to decide between which one you want to use and help you to notice things that are important. So if two things can differ in a particular way, then that way is an important thing to think about. How do people feel about what I just did? What's a confidence interval? Now that is in this course. Cool. I'm going to come back to confidence intervals if that's okay. I'll just talk about it now. The idea is that a confidence interval is answers the question of what is this number, and it gives you a range of possible answers. So for example, I could ask, what is the difference between the proportion of feel hot with chili and the proportion of people hot without chili? That question, what's the difference between the proportion of people who feel hot with chili and the proportion of people who feel hot without chili? That's a question about a single number that describes all possible people who could be eating meals with or without chili. And so a confidence interval, we'd be asking ourselves, well, the proportion with hot with chili might be proportion number 1, and the proportion hot without chili might be proportion number 2, and then the difference would be like proportion 1 minus proportion 2, and then I might say a 95% confidence interval is like from 0.01 to 0. This is a made up number, I'm just pointing it out. 0.05 to 0.13 or something like that. And so this would be saying that the difference between the proportion who feel hot with chili and the proportion who feel hot without chili is between 0.05 and 0.13. So saying that the proportion who feel hot with chili is between 5 percentage points higher or 13 percentage points higher than the proportion without. That is a confidence interval. And it's calculated based on you imagining there's a particular difference that came out in your particular data, and you're imagining all of the, you're going a little bit down from that and a little bit up from that to try and give you an estimate for what the true proportion is for all possible people. That's the idea of what a confidence interval is for. How do you feel about that? Yeah, that sort of thing. Like it would be like, yeah, our studio would do it for you, but it'd be like P1 hat minus P2 hat plus or minus Z star times something in this spot. Yeah, well, no, that one you're thinking of is for the means. This one's for proportions, so it's different. So anyway. So there are multiple Z tests, and this might not even be in your course, so I'm not sure. There are multiple tests that have a Z in them in the world. Okay, so I'm going to move on and actually go back and talk about the actual Chi-Squared test now. So the Chi-Squared test goes both mean and proportion. Awesome, thank you. Every statistics course, every unit degree has a research methods or statistics course, and they're all a little different. So that makes my job hard. Okay, so we're at the Chi-Squared test, and we know the kinds of questions that it can answer. But what we haven't got is how it goes about finding that answer. And being a test, it will produce a p-value. They always produce p-values. And so, as with all hypothesis tests, the general idea of a hypothesis test is that you have a null hypothesis. And that null hypothesis allows you to imagine all the possible sets of data you could have had, assuming that the null hypothesis is true. You don't really do this, but this is where the idea of how a hypothesis test works. And then you imagine a particular single calculation that you could calculate from any data you could have had. We create this thing called a test statistic. And a statistic, the old meaning of the word statistic means thing that you calculate from data. And it's called a test statistic because you're going to use it to do a test. And so you calculate a test statistic, you imagine all the possible test statistic answers that you could have had based on all the data that you could have had. And those things have a distribution, and you compare the one you've got to all the ones that you could have had. And you get a p-value. And the p-value is the probability of your test statistic being further away from usually 0 than the one, your p-value is the probability of all the other possible test statistics that could have happened being further out from the center than yours. That's how a null hypothesis, that's how a hypothesis test works. Some people call them significance tests. I call them hypothesis tests. And they work this way. All right, so for your chi-squared test, each of these have particular things. The null hypothesis for a chi-squared test goes the two variables are independent. And the alternative hypothesis goes the two variables are not independent. In case you're wondering, all the vowels in independent except the first one are E's. It doesn't have an A in it. So just for spelling purposes. Not that it matters that much. They're not really marking you on your spelling. So that's the hypotheses that go with the chi-squared test. What I'm going to point out is that when it says the variable, what it doesn't mean is the individual answers to these questions. So if I look here, the answers here are yes and no. It's yes is not a variable by itself and no is not a variable by itself. The whole thing of whether they feel hot or not, the question itself is the variable. So does feeling hot or not make a difference to, is that related to having chili or not? But it doesn't have to be two categories and two categories, and I'll do one that has different numbers as well. Okay, so that's the beginning of that. The next thing is we have to imagine all the possible data we could have had. And to do that, we're going to actually have to set up our data in order to do this calculation. So we're going to put the data into a two-way table. Is that what your lecturer calls it? If you're Googling things online, sometimes they call it a contingency table. If you ever want to look it up. And even some places call it a confusion matrix. So, but that's rare, but I like it. Okay. And so it'll be something like this. It doesn't really matter how many categories it has. And so you have like A, B, and C, and yes and no, something like that. And my example's only got 2 options for one of them and 2 options for the other. But it could be any number on either one. And there'll be a number of people or petri dishes or jelly beans or whatever it is that they are in these spots. And then you can create the totals as well if you want. And then there'll be a grand total here. So that's what you're going to do. And this isn't actually even doing the calculation yet. This is just setting it up. Because your original data doesn't look like this. Your original data in, say, RStudio would be a list of every individual and what their answer was for the two things. So I just want to point that out. The data is usually like person 1, and it'll say like the letter and the answer that they had. You know, this person's got A, this person says yes, this person 2 said B and they said yes as well. Person 3 says A again, and they said no, and there's like, they said C and they said no, and it'll be a whole list like this, and this needs to be turned into this in order to do the calculation. If you're using RStudio, you don't have to create this yourself. The RStudio can do that on its own. Yeah, but this is what it would probably look like when you collected the data. You would write down each person, you would write down what the two answers for the two variables were. All right. So I'm going to change my situation. Maybe it's not going to be I gave them chili or not chili. One of them is going to be no chili, one of them is going to be chili powder, one of them is going to be chili flakes, and I've got 3 options, okay? Or chili sauce. So you've got to imagine that it's a possibility. Okay, that's the beginning of calculating this. We take our original data about our individuals, we put it in this table, we count how many people who say A say yes. So far we've got 1 here, and 1 person who says A and no, that's here. 1 person who has B and yes, 1 person who has C and no, and you just fill out the whole table based on the list, and the computer can do that for us. And then what we have to do is we have to imagine what could have happened. So if we just suppose that we had a different group of people, but they had the same totals, and we imagine what could have happened in this spot here, that's what we're going to imagine. We're going to imagine all the things that could have happened and to arrive at the same totals. It seems like a weird thing to do, but that's the way it's done. Pearson, back in the day, just discovered that this was not the worst plan. So imagine all the things that could have happened. Because the idea is that if being in one of these categories A, B, C doesn't make a difference to the yes or no, then it's really just one giant group. It doesn't matter which A, B, and C you're in. You'll always have the same chances of being in the yes or no. So I could shift the people in this row back and forth among the different A, B, and C categories, because they would have said yes regardless of which category they're in. If really the letter doesn't make a difference to the yes or no, then the people who are in this top column, top row would have said yes no matter which category they're in. So I could move them all around here and it wouldn't make any difference. And that's the idea that we're going to do here. But also, I probably set up this experiment to have a certain number of A's and a certain number of B's and a certain number of C's. So I need to have the same number of these here. So I'm imagining moving the people all around in these different spots and thinking, well, what would the total what would the proportion in each of these boxes have been if I had allowed the people to be in different spots? That's the idea. But I don't have to do all of that. What I do is I say, well, what would I have expected to happen if there was no difference? So here's an example. I'm going to have to add these up. I made it hard for myself, didn't I? That's 36. 18 and 6 would be 24. Okay, so here is some made up data. So I can imagine this is what I observed. I can imagine what would have happened if I had what I could expect to happen if it didn't make a difference which group was in what. You don't technically need the totals, but I just want to make a point. So if I ignore which group, ABC group they're in, then 36 out of the 60 people said yes, and 24 out of the 60 people said no. So if which category you're in isn't related to whether you say yes or no, that same percentage of 36 out of 60 should be here as well. If slightly more than half of them say yes across the whole of them, it should be slightly more than half here and slightly more than half here and slightly more than half here. That should be the same in all three categories. And so I can go, well, this fraction, 36 out of 60, that fraction of this 20 people should be what's in that spot. If saying yes or no doesn't make it, isn't related to saying A, B, or C. And so that will be 12. That's what I'd expect to be in that spot. And this spot here, for example, I'd expect, well, there's these people saying no, 24 out of 60 people say no, and that fraction of the 21 people in group C should produce the right answer. And this will work out to whatever it works out to. I don't know what it works out to. 4. So that's what calculators are for. I get 8.4. And it's okay to have a decimal because we're saying what would I have expected to be in that spot on average across all of the possible ways of rearranging these people. And I can do that for all 6 of these spots. How are people feeling about what just happened in that calculation? So what, I'll just give this another. So what I will say is that most resources that teach the Chi-Squared test say that to figure out what's in this spot, you need to do the row total times the column total divided by the grand total, and that will produce the same answer. Because this is all multiplication and division, it doesn't really matter what order it happens in, it will produce the same answer. I could just as easily done 20 divided by 60 and that times 36, and it would have produced the same thing. And so that's a shortcut version, this times this divided by this, but I have trouble remembering that, but I can remember this fraction of this group should be there. Yeah. So you're supposed to do that for every possible spot in this table. And well, the computer does it for you, of course. That's the by hand version is to do that calculation. And so I can do, this spot will be, well, still adds up to 20, so I know this is going to be 8. And this will be whatever it is, whatever's left. 24 minus 8 minus 8.4 would be 7.6. And then come down 7 is 12. Okay, so this is what would have happened if I did all those calculations separately, and I really want to just check one of them to make sure I'm getting it right. All right, okay, cool. I made a little shortcut there. I don't know if you noticed it. I had 2 of these, and I know that they still have to add up to 20, so this one must be 8. That one's 12. And these still had to add up to 21. And these had to add up to 24, so I could figure out the missing pieces. And that's an important thing that I want to point out, actually, so I'm glad I did it. So I'm only part way through calculating the chi-squared test here. Luckily, computers can be taught to do this, so that's why we have things like RStudio. The next stage is to compare what I did observe to what I would have expected on average, if they really aren't related. And so I have to see how far apart these numbers are. And so what I'm going to do is I'm going to go observed minus expected and square that and divide by the expected. Because Pearson, back in the 1910s, decided it was a good idea. It was very clever, was Pearson. Yeah. There were 3 or 4 main people back in those days who were working on these brand new statistical tests after they invented hypothesis testing. Some really clever stuff. So technically, we're supposed to do a brand new table. The contribution to the chi-squared test, chi-squared statistic. Which is observed minus expected squared divided by expected. Here we go. I don't need the totals anymore to do this. So I've got 5 minus 12 squared divided by 12. And that's what goes in this spot here. That's what goes in that spot there. And then in this spot here, that one will be 13 minus 11.4 divided by 11.4. Oh, sorry, 11.4 squared. And that's what will go in this spot. So you compare the 2 tables to each other. In every position, you find the matching 2 numbers, and you do this calculation. Well, the computer does it for us, but, you know, we know that it's there. And we have to do that for every box, which I don't want to do. We have to do that for every box, and these are called the contributions to the chi-squared statistic. So this position here contributes 4.083 to the chi-squared statistic. This position here contributes 0.225 to the chi-squared statistic. So far this box is adding a lot more than this. And the reason it's called the contribution is that to get the actual chi-squared statistic, I need to add all of these up and total them all, and that's the chi-squared statistic. Cool, huh? You okay? No, it's just the sum. Because you've squared. Because of these squareds here. Presumably, back in the day, there was just a chi distribution. And yeah, it's called the chi-squared statistic because it has a chi-squared distribution. And presumably back when Pearson invented this, there was such a thing called a Chi distribution, and it might still exist, but it's not very common. Yeah. I would assume so. Okay. That's the thing. So I would have to do that actual calculation in order to do this. I would have to add all of those things together. So I don't feel like it. Yeah. So all of these boxes have numbers in them. Give me a moment. Okay, so I'm getting that the final answer is 16.556. And these numbers here are all, I can actually fill them in now. This number was 4.1. I'm just going to do them to one decimal place because I can't fit them in otherwise. This one's 0.2. This one's 2.3. This one came out as 6.1. This one came out as 0.3. And this one came out as 3.5. Okay. Oops. And then when you add them all together, you get 16.6. This is the test statistic. So just a second, where are we up to in our list of things? We had null hypothesis. We had to imagine all the possible data that could have been, and we imagined that all these people or objects moving around within this. And then we had to calculate a test statistic, which we've done. And we have to imagine all of the possible test statistics that could possibly have happened if the people had been arranged differently. That's what we have to imagine. Now, we don't have to because Pearson figured this out 100 years ago. So almost exactly 100 years ago. So, yeah. So what I'm going to say is that this whole process here of starting with the data I've got, doing the expected, doing the contribution to the chi-squared and adding it all up, that's the thing. We have to imagine what would have happened if this data had been arranged differently, all the possible ways this could have been arranged under the assumption that these are independent, and all of the test statistics that could possibly have happened in that situation. And when we imagine all the test statistics that could possibly have happened, they form a distribution. So when we talk about the distribution of the test statistic, what we're thinking is all values of this chi-squared that could have happened. With information about how likely they are if they happened. And a distribution is a list of probabilities, really, and there are plenty of them that have names, so that if you said to a statistician, oh, it's a chi-square distribution, or it's a normal distribution, or it's an F distribution, or whatever, they would know exactly what that means and know how likely everything is. And so it's called a chi-squared statistic because it has a chi-squared distribution. So the distribution is a chi-squared distribution with some number of degrees of freedom. I'm pretty sure that your lecturer will probably write it as a chi-squared with a number at the bottom just here. Could be wrong. Or maybe we'll just say the degrees of freedom is equal to whatever it is. Chi-squared distribution with some number degrees of freedom. The phrase degrees of freedom is not necessarily a useful phrase. Let me put the camera back. It's not necessarily a useful phrase. It gives you this idea of somehow having freedom to move or change things, and that is actually the truth. Let me show you something. Back here, when I had filled in this one and this one, knowing that the row and column totals were, that allowed me to figure out what all the other numbers were. So once I had chosen that this was 12 and this was 8.4, I had to have all these numbers be what they were. So I'm only free to choose 2 of these boxes before all the rest have to be whatever they are. In the chi-squared test, that's the degrees of freedom. The number of boxes you can fill in the table and still be able to figure out what all the rest are just from the row and column totals. So it's 2 degrees of freedom for this story. And in my head, I'm imagining the table without the row and column totals, and I'm crossing out 1 row and 1 column, and the number of boxes left, that's the degrees of freedom. In your notes, they say it's the number of rows minus 1 times the number of columns minus 1, which is exactly what that picture is. I remove 1 row, that's this bit. I remove 1 column, that's this bit, and I figure out the number of boxes left in the corner. That's what you get by timesing them. For some reason, this calculation does not stick in my head very well, but this does. And it's literally the number of boxes you can change before everything else has to be whatever it is. I'm just going to point something out about degrees of freedom. With the t-test, the degrees of freedom is n minus 1. That's because if you know what the mean is going to work out to be, then you can choose all but one of them, one of the numbers, and there's only 1 number left that you can change. But you can change, once you can change all but one of them, and then that last number has to be whatever it is, or the mean's not going to work out to whatever the mean worked out to be. And so that's why it's n minus 1 for a t-test. That reasoning for what the degrees of freedom are doesn't really apply to other situations, I'm sorry, it just turns to crap. But this works for the chi-squared test. And so I need to know if the chi-squared test with 2 degrees of freedom, not test, damn it, if the chi-squared distribution with 2 degrees of freedom is the distribution that describes all of the test statistics that could have happened, how does my test statistic that actually did happen compare to all the ones that could have happened? That's what I want to know. So I'm going to need to ask my computer to help me with that. But before I move on, how are people feeling? I'm glad it makes sense to at least one person. Okay, so I've done the part where I imagine all of the things that could have happened. So I did this bit, I did this bit, I did this bit, and I did this bit. So that's where I am. Now I need to figure out the p-value, which is a comparison between what did happen to all the things that could have happened. So these are all the chi-squared statistics that could have happened. They start at 0 and they can be as big as you want. and I can draw as a height how likely they are. I think that's what the chi-squared distribution with 2 degrees of freedom looks like. And here's my, I don't know what these numbers are, but here's my 16.6. This is the one I actually got. And these are all the things that they could have happened. And it's much more likely to be down here than it is over here. That's what this height is. And so I'm interested in how likely it is for it to be worse than this one. So if the expected thing that I expected to happen on average actually happened, then the difference between each of these and the expected would be 0, and the answer for the chi-squared statistic would have been 0. And the further apart these are, the bigger the answer is going to be for what you get when you minus them and square them. And so the further away from the expected, the worse, the bigger this number is going to be. So I'm interested in all these numbers, which are the ones that are worse than mine. And I want to know how likely is it to get a number worse than mine. That area, that's the p-value. Because the area above something is the probability of that zone happening. And that's what, I mean, it's not really drawing a picture and colouring it in and figuring out the area, but that's what R is doing. It's giving you that answer. I can't do it from my drawing. But my p-value comes out to 0.00025. It's probably way too many decimal places, but that's what it is. I put in chi-squared.dis.rt, which is the right tail. I mean, I could have done this in R, but I didn't have R open, and I couldn't be bothered waiting for it to run through its whole I'm getting ready thing. E5 is where the statistic was, and the 2 is the degrees of freedom. And the R command works, so just a second, no one who's in the Zoom can actually see this, just a second. I was in Excel and I had calculated this number just here, according to this formula here. The R command is similar. Yeah, your lecturer probably wants you to be able to use R. The R command is probably P chi-square brackets number and degrees of freedom. Oh, well, that's the chi-squared.test. I was doing the chi-squared distribution. So. Anyway, as I said, there's lots of different programs in use. The economics statistics course uses Excel in first year. Okay, so that p-value is the probability, the formal probability notation is that the probability of chi-squared being greater than 16.6. That's what this is. That's the probability of being worse than what I've got for my data. And so these are all the chi-squares that could have happened here, and this is how likely they are, and these are the ones that are worse than mine. And there's only a 0.00025 probability of being worse than mine, and so I declare that mine is pretty bad from the perspective of thinking that they're independent. So p-value is very low, so therefore reject H0 and conclude, damn it, conclude that the letter is not independent of yes, no. Probably from, no, just a second. The letter A, B, C, and the response yes, no are not independent. That's the best way of doing it.
So for you to reject that value because it's really small, what is an indication number whether you reject or accept?
Yeah, because normally someone tells you that you want to do it at the 5% level or the 1% level. So I just said very low, but usually you'd say, yeah. So at the 5% level. But it's also less than 0.01, so I could reject it at the 1% level if I wanted. But you usually do whichever one that the lecturer actually asks you to do. In medicine, they traditionally do 5% or 1% if they're being really stringent. Now, I just made up this data, like, you know, and I deliberately made it so that it was extremely obvious that it's much more likely to say yes when you're in C than it is to say yes when you're in A. I can see it from the table. 18 compared to 3 or 15 compared to 5. But the contribution to the Chi-Squared test gives you a little extra information. Where'd it go? Must be here somewhere. Here it is. This 6.1 is the biggest of these numbers. That is the one that is the most different for what I would have expected it to be. So I'm saying that if they really were independent, then this is the most surprising. The fact that the people who are in category A are much more likely to say no than the other categories are. And the people in B are acting pretty much as expected, and the people in C is much less likely to say no, and the people in A are much more likely to say no. Because people only use the 5% level because Fisher did when he invented hypothesis tests back in the 19-teens. Got to pick a number. How are people feeling? Do people have any specific questions about the pieces of the Chi-Squared test that I haven't mentioned or that I have mentioned? So the question I've got coming in the chat is that what's the purpose of calculating the Chi-Squared contribution? And that is not a dumb question. My understanding is, and I'm still not 100% sure of all the details, firstly, you have to calculate it to get the Chi-Squared test in total. You have to calculate them all because you need the total to get this. But normally the computer does all that bit for you, and so you're asking why would you calculate these individually even though the computer's done all that behind and hidden it from you to calculate this Chi-Squared statistic overall? And I think the answer is to know which of these is the most different to what you would have expected. And so the largest part of the Chi-Squared statistic is coming from here. So it tells you which category is more different than the others. So the overall p-value just says that, yep, being in category A, B, or C does make a difference to how likely you are to say yes or no, but which category makes the most difference to that? And it says that being in category A makes the most difference because it has the highest contributions to the chi-squared test. That's my understanding of it. There's a few technical details in there I'm not sure of because it's like, yeah. I think it only helps if one of them is way bigger than all the others. And so if they're all pretty similar, then yeah. So you're not sure about this degrees of freedom? So there are two ways to calculate it. One is to draw the table without the totals, cross out one row and one column, and the number of boxes that are left, that's the degrees of freedom. But the alternative way is to say, how many rows have I got? I've got 2 rows. How many columns I've got? I've got 3 columns. And go 1 less than the number of rows, which is 1. That's what this R minus 1 stands for. And 1 less than the number of columns, that's 2. And times them together, that gives me 2 degrees of freedom. That's right, table method, I just need to cross out one row and the outer row and the outer column and count the inner boxes. Yep, exactly. So for example, if I had had a table like this, I could cross this out, there's 6 boxes less, so the degrees of freedom will be 6. Ooh, okay, I've just got a question here. How to conduct a chi-square test for rolling a certain value on a fair 6-sided die with 1/6 probability. Did you do the chi-square test for goodness of fit in this course? Are you able to share with me more specifics of that question? Because I'm not 100% sure what's going on with that one. Oh, okay. Just going to pause for a second while you sort that out. Okay, so we're back. All right, so this is a chi-squared test for goodness of fit. So I will talk a little bit about that. But first let me read it. A 6-sided die is rolled, the following observations are made. The following null hypothesis was considered, where PI is probably rolling the number I. Calculate the expected number of times you would roll a 1 given the null hypothesis. So given that all of these numbers have the same probability, I'd expect all of those numbers in the boxes to be the same. So how many are there in total? There's 20, 30, 40, 50, 60 of them. So I'd expect them all to have the same number, and 60 divided by 6 is 10. So that's cool. So what are we going to do with the rest of it? I'm going to write some, I'm just going to write some things down. All right. Okay. This is a whole other chi-squared test. The other one is technically the chi-squared test for association. This is the chi-squared test for goodness of fit. And the way that this test works is that you don't have a 2-way table, you only have a 1-way table. And you have a list of various categories. So let me just talk a little bit about how this test works. It doesn't have to be people, it could be dice, or it could be whatever. And there is one variable, which is a categorical variable, and it has various categories. And you're not asking whether it's related to anything in particular, it's just there. And what you're doing is you're relating it to what you think the probabilities of being in each category is. So your question is it this? Is it this set of probabilities? So I might think that A, B, C, and D have this probabilities. It's half A. I do not want to do it in fractions. It's 0.5A and 0.2B and 0.1C and 0.1C. That does not add up to, right, 100%. I might think it's this set of probabilities. So maybe I've got a die that's with the, like in this example, a die that's supposed to come out with 6 numbers and they've each got a probability and I think they should all be the same. Or maybe I've got some thoughts about how likely people are to choose certain letters. I mean, if they were the letters of English alphabet, then E would be the most common. And I just want to test to see if the ones I've got match the same probabilities or whatever. But it's not a question about a relationship, it's just a question about what actually is there. And so what you create is in some way a one-way table. The other one's a two-way table, and you just have the categories and you write down how many there are. So maybe there's, 30 here and 6 here and 10 here and 20 here. And I get 20, 30, 60, something like that. And I could ask myself, well, I can figure out the percentage in each spot and I compare it to these percentages. That seems very like the sort of thing I'm doing in the two-way chi-squared test. Maybe I could do the same calculation and do observed minus expected squared divided by expected and see what happens. But I'm going to need to know what the degrees of freedom are. Okay, here we go. In this situation, the degrees of, so I'm going to do exactly the same calculation I did before. These are the expected. These are the observed. But the observed actual proportions, these are not the expected ones, these are the proportions. I'm going to need the expected, aren't I? So the expected total's still the same. This spot, there's 0.5 of them are supposed to be A, so 0.5 of the 66 are supposed to be A. So this would be 33 in this spot, that's what I'd expect. And then the B should be 0.2 times this, which would be 12. Is that right? No, that's not at all correct. 10% would be 6.6. 2 of those would be 12, 13.2. This one's also supposed to be 13.2, and this one's supposed to be 6.6, and these should all add up to 66, hopefully. Okay, and then I still do the observed minus expected squared. So the chi-squared statistic is the observed minus the expected, damn it, just a second. Chi-squared contributions. I know that your lecturer probably doesn't call it this, but it doesn't matter. I've just given it a name. So this would be the observed minus the expected squared divided by the expected. And that would come out to whatever it comes out to. So that's really a very small, oh damn it, that doesn't look at all good. That's really a very small number. So this is quite close to what I would have expected it to be. So this one comes out as 3.93. So 0.78. This one is 27.21. So this one's the most different to what I would have expected. It's huge. And so my chi-squared statistic is the sum of all of those things. I haven't answered the question of the degrees of freedom. I just wanted to do the whole thing. That's not 2.3. It's 2.7. Sorry. Not that it's going to make too much difference. That's a very large number for a chi-squared test. It's going to come out significant. And now I need to know the distribution. You know how I said the thing where you need to figure out how many boxes you can fill in before the rest of the boxes are definitely sorted out? Well, I could fill in all but one of them, and then this one would be fixed. If I only filled out two of them, these could be anything I wanted. Like if I know that these are 30 and this is 6, then I could switch these people up however I want. But if I fill in 3, then the last one has to be whatever it is. So the degrees of freedom is 1 less than the number of boxes there are. There's this many boxes. I will cross out 1 row, 1 column, and the degrees of freedom is 3. Always that way. In the example we had before, where there were 6 boxes, the degrees of freedom will be 5. So then I'd look this up in the chi-squared distribution with 3 degrees of freedom, and it would be all the way over here. And the p-value would be extremely small. And I'd conclude that actually, no, that is not the list of probabilities. And in fact, it's much more likely to have D than that list of probabilities suggests, because that's the one with the biggest number. So with your dice, the degrees of freedom is 5 because there were 6 options. So the general rule is remove 1 row and 1 column, but if there's only 1 row, don't remove it. You have to leave something. How do you feel about that? So it turns out there's 2 chi-squared tests, and they're called chi-squared tests because they use a chi-squared statistic and a chi-squared distribution, but ultimately the goal of them is different. This one has 1 category and I'm comparing it to a list of probabilities that I think it is, and this one has 2 categories and I'm seeing how they're related to each other. 2 sets of categories. It's time for ANOVA. We have just enough time to talk a little bit about at least what they're for. So you've learned 2 flavors of ANOVA in this course, and in a technical sense, the word ANOVA turned up in regression as well. inside the RStudio, but it wasn't really ANOVA. So ANOVA is short for Analysis of Variance, which is weird, but it sounds fancier than AOV. If I did a proper acronym, AOV. So Analysis of Variance. I say ANOVA and put the emphasis on the O. Some people say ANOVA. Wingardium Leviosa, not Wingardium Leviosa. No one cares. Say what you want. So ANOVA, both of the types of ANOVA are designed for this situation where your individuals, they don't have to be people, but it's easier for me to draw people. I can draw stick figures, have a numerical variable. They have a number outcome. And this is how I draw numbers in my pictures. I put a little scale upon which the number is drawn, as opposed to boxes, which is what categorical variables are. You need to be thinking of a number outcome. You could be measuring the temperature of people as numbers. You could be measuring the weights of your little chickens as they're on different types of food. You could be measuring how long it takes for your surgeon to do his surgery. You could be measuring the heights of trees. It doesn't really matter, but it has to be a number. And you're interested in what things affect that number. So the other things that you have is some sort of category. Doesn't matter how many categories it has, but in general, you would like there to be at least 3. And what you're interested in is how this number changes when you move from one category to another. And everybody's in their own separate category. You do not have the situation where 2 people are in the same category, where one person is in 2 different categories, or where one chicken is in 2 different categories, or one tree is in 2 different categories. This is the situation when you do one-way ANOVA. That's the situation for one-way ANOVA. I draw these pictures to help me make sense of the story of what's going on. So with my chili experiment, maybe I give them, no chili or chili flakes or chili sauce, and then instead of asking them, do you feel hot, I literally measure their actual temperature so that it's a number that I'm recording about each person as the outcome, as opposed to just a category. Or maybe I give people 3 different kinds of treatment. I do nothing. I tell them about, I give them, I give them psychotherapy. This one I give them psychotherapy and drugs. And then I measure, I do some fabulous 40 question survey and add up a score and decide that this score represents their level of depression. And that would be this I could do as well. But that's what ANOVA is designed to achieve. I'm going to answer the question that was asked right at the beginning, which is what's the difference between one-way and two-way ANOVA? I'm going to answer it now. And it's to do with the kind of data you've got and the kind of question you're asking. This is one-way ANOVA. Two-way ANOVA works like this. I'm not going to draw this one. I'm not going to draw the people. You're just going to assume that they're there. Two-way ANOVA is designed for this situation. Doesn't matter how many categories there are in each of them. One-way ANOVA is designed to see how one set of categories makes a difference to a number. Two-way ANOVA is designed to see how two categorical variables make a difference to a numerical outcome. It's called two-way ANOVA because there's two ways to affect the outcome. That's the difference. There are some serious differences in how in how much calculation is required, but that's the main difference between them. It is not at all like match pairs testing. Can I show you the match pairs thing? So I mean, yeah, it's more like the difference between simple regression and multiple regression. So simple regression has a number in both of these spots, and multiple regression has numbers in all these spots. And so actually it's exactly like simple to multiple. I'm just going to, while I'm talking about it, just mention something. In case you're wondering how this would look for some of your other ones, a t-test has a numerical outcome. It has a quantitative outcome. It's you measure a number on each individual, and you're interested in how a category with two categories affects that. It's either yes or no, or A or B, or before or after, or placebo and drug, and you're interested in how these are related. And what you actually ask yourself is the mean of this number in this situation different to the mean of this number in this situation? That's what you do, but the overall question is, does this category make a difference to this number? But you have two ways of setting up that data. It may be that some people are in this category and some people are in this category, or it could be that everybody is in both categories and they have this outcome measured twice for every individual. They're the difference between an I don't know what this is called in your course. Some people call it an unpaired. This is always called a paired t-test. Some people call this an unpaired t-test. Some people call this an independent samples t-test. Some people call it a two-sample t-test. Okay. They are the same. The data will look extremely different. The data for this will tend to look like person 1, 2. This is the person, and it'll be 1, 2, 3, 4. And then you'll say this is the outcome in category A, situation A, and it'll have a number. And this will be situation B, and it'll have a number. That's what the data will look like for this, because each person, no, crap, wrong entirely. Each person will have one situation of their own, in A, B, B, and they'll have a number to go with them, which is the outcome in that situation. Whereas this one, your different people will situation A, and they'll have a number for what happened when they're in situation A, and this person will also be in situation B, and they'll have a number for what happened in situation B. The data for this will look like this, because this is what we write down for each individual, 2 numbers in different situations. Whereas in this one, for each person, we write down what situation they're in and what the single number was. Yeah. But I find it easier to draw this picture than to look at the data. But just so you know.
How does two-sample t-testing differ from
Okay. How does the two-sample t-test differ from two-way ANOVA? Well, firstly, the two-sample t-test only has one thing affecting the outcome, which is whether you're in this category, which category you're in here. Whereas two-way ANOVA has 2 things affecting the outcome. The difference between the two-sample t-test and one-way ANOVA is that one-way ANOVA has any number of categories here, and the two-sample t-test has only got 2. Yes or no? These are important questions. Any two of the tests that you've learned, you can say, how are they similar, how are they different? So ANOVA, one-way ANOVA and the two-sample t-test are answering the same question. It's just that the two-sample t-test has only got 2 categories, whereas ANOVA can have any number of categories. You can, in fact, do one-way ANOVA in this situation if you want, and it will give you the same p-value as the t-test. Yeah. Although later on, after the t-test was invented, they managed to make adjustments for if the two groups don't have the same variant, but they haven't made adjustments for that with one-way ANOVA. So I think they do the Welch to suit, yeah. Okay, so that's the goal of ANOVA. The way that you do the ANOVA, now let's go back to our list of how to do a hypothesis test. ANOVA, in many ways, is like the Chi-Squared test, actually. There's my list of how you do a hypothesis test. This. So one-way ANOVA. Which is designed for this situation. I'm just going to do it with 3 if that's okay, because maybe I'll do it with 4. So every individual has a category that's recorded about them, and every individual, nobody's in 2 different categories at once. So the situation is that everybody has the category recorded about them, and they also have a number recorded about them. Okay, that's what it's designed for. Okay, I need a null hypothesis. So the null hypothesis is that all of the means, so I imagine that all the people that belong in this category, they've all got numbers, and those numbers have a mean. And I imagine that the mean for all possible people that could possibly have been put in this category, that is mean number 1. And then there's a mean for category 2, and there's a mean, I'm going to call the categories A, B, and C, and D because they're not ordered. You could call them mu1, mu2, mu3, and mu4 if you wanted. You can call them mu A, mu B, mu C, mu D. It doesn't really matter. But the null hypothesis is that all of the means are equal. You can write it this way, or you can specify what the means are called and say the null hypothesis is that all the means are equal. The alternative hypothesis is that not all means are equal. These things are called parameters, by the way. A parameter is an unknown value that belongs to all possible individuals. So this mu A is not the mean from my data, it's the mean for all the people that could have been in my experiment. Do not write mu A is not equal to mu B is not equal to mu C is not equal to mu D. That's not the same as the opposite of this thing. You're not declaring that they're all not equal to each other. You're just declaring that it's not the situation where they're all equal. It could be that 3 of them are equal and 1 of them is different. And that's a possible thing that's okay. All right, I've done a null hypothesis. We imagine all the data we could have had. So we imagine that every individual has a value, and that the individuals each have so just a second. If all the means are equal, then it's really just one giant group. It doesn't make the slightest bit of difference which category you're in as to what number you get. It's just random as to what number you get. And so if all the means are equal, there's just one great big group. And so the fact that group A has whatever mean it has is just because you randomly put people in group A. Yeah. And so we want to imagine all the things that could have happened and compare them to what did happen. Pardon me. We need a test statistic for that. And that test statistic is going to be called an F statistic. F for Fisher, who invented this test. Actually, I just read a story the other day about Gossett, who invented the t-test. And someone said to him publicly, "Thank you so much for all the work you've done for statistics." And he said, "Oh, that's okay. Fisher would have figured it out by himself anyway." So there you go. Gossett was a very nice person. Fisher, not so much. He was okay, but Fisher had the tendency to refuse to explain anything that he thought was obvious. Like many academics, I guess. Okay. So we're going to have to find a way of calculating the data. And there's a lot going on here. What we're going to do is we're going to have to calculate the group mean for each individual group. I don't know if you want me to explain this. I've only got like 5 minutes to go. But you calculate the group mean for each individual group. You calculate the grand mean for the whole big group, because that's what we're imagining. If ABCD doesn't make a difference to the number outcome, then it's just one giant group, and so we can just do one giant mean. And we figure out how far everyone is from their group mean and how far everyone is from the grand mean and how far the group means are from the grand means, and we compare all those numbers to each other. There's this big calculation we do from all of those numbers. Do you want me to talk more specifically about how that calculation is done? How do people in the Zoom feel? Okay, cool. So what we're imagining here is that we've got 4 groups of people, or they might not be people, they could be anything, and every one of them has a group mean. The lecturer probably calls it Y, don't they? Just a moment, just want to check. Yep, they call it Y. Good. Lost my Zoom meeting. Right. They call it Y because it's an outcome. You know, when you do calculations and you go Y equals something involving X, that's why they call it Y, because there's X's here and they produce Y's here. But you can also do all of them together in one big group and do just Y bar, which is the grand mean. Okay. And then for each individual, we're going to figure out how far they are from the group mean and how far they are from the grand mean and how far the group mean is from the grand mean for that person. So for this person, we're going to figure out, and they're in group A, I'm going to figure out how far that person's value is from the group mean. And just let me draw the pictures here. These are the numbers. Here's maybe the group mean for A, and here's the group mean for B, and here's the group mean for C, and here's the group mean for D. And maybe somewhere in the middle here is the actual grand mean. And then here's each individual. This person's in group A, and maybe they're just here. And this is the Y for this particular person. I want to know how far this is and how far this is, and how far this is for that person. So this person's going to have a y minus ya. And I'm going to square everything because, well, this is what Fisher said is the best plan. And they're also going to have a y bar, a ya minus y bar squared, because subtracting things is how far apart they are. When you subtract things, it tells you the distance between them. And I'm also going to calculate how far they are from the grand mean as well. These three things are all going to be calculated. And then for the next person who's in maybe in group B, it'll be y minus yb squared, yb minus y bar squared, and y minus y bar squared for this person here. So this is person number 1. This is person number 2. And so on. I'll do that for every person in the entire big study. And then I'll add them all up. This one, and this one, and this one will do the total. Are you ready? Right. This is called, give me a second. Not that one. Right. Right. Well, I lost my Zoom again. These are all called sum of squares because these are squares and we've added them up. This is called, all right, so just a second. We're trying to imagine a model, a situation where if which group you're in does make a difference, then the best estimate for the average for each individual person is their local group mean. If each person, if which group you're in doesn't make a difference, then the best estimate for what the average value is just the grand mean. And then there's a bit of difference here. So the concept that we're thinking of is that when the universe chooses what this person's value is, first the big distribution decider person says, okay, we'll first do the grand mean, and then we'll go a little bit further to get to their local mean, and then there'll just be a bit of random crap to get what their actual value is. And so for this person, we'll go the grand mean, and then we'll go a little bit further to get their group mean, and then there'll be a little random crap that will get their actual value from there. And sometimes that random bit is positive, sometimes it's negative. And so this bit here, how far everyone is from the group mean, is called the error. Or possibly residuals. And this bit here is the model. And this bit here is called the total sum of squares. So in some resources you'll find online, this will be called SSE, and this will be called SSM, and this will be called SST. In case, I don't know if it's called that in this course, I'm pretty sure it's not, but just so you know, if you're looking up ANOVA online, that's what will be in those spots. And what will normally happen is you'll see these totals drawn in a table. Like this. So there'll be a number for the sum of squares here, there'll be a number for the error here, there'll be a number for the total. That's what all these things add up to. They go in these spots. There'll be a thing here that says the degrees of freedom. There'll be a thing here that says the mean square things. And the calculation goes. Now, degrees of freedom is the amount of information you have once you've chosen everything. So the total amount of error degrees of freedom here is that once the total big grand mean, once everyone but one person you've chosen their number, in order to keep the same mean, there's only one person left, and they will have exactly what number they need to have to make the mean whatever it is. And so the total thing there is the total number of people minus 1. That's the degrees of freedom that goes with the total sum of squares. The model, these are all calculated from the local group means. Once you've chosen 2 of them, then the other one will have to be whatever it is in order for the grand mean to work out to the same thing. And so this is going to be the number of groups minus 1. And then the error will be all the ones that are left. So whatever this is minus that goes in this spot here. And then the mean squares, if you go this divided by that, that will produce this answer here. That's the sum of squares divided by the degrees of freedom. And this is its sum of squares divided by the degrees of freedom. And then the F statistic is this divided by that. That division goes here. And that is how you calculate the test statistic. It feels like the Chi-Squared statistic, but worse. It's a very complicated calculation, which is why the computer does it for you. Imagine Fisher in 1920 inventing this and not having a computer. Okay, the ultimate goal of this F statistic is to compare how far this top line is how far everybody is from their group mean. So this top line is how far all the group means are from the grand mean. This second line is how far everyone is from their group mean. So if the group means are all really far away from each other, compared to how far the individuals are from their group mean, this will be a big number. And that'll tell you that all the group means really ought to be different. Yeah. So I like to draw a picture like this. And this is the outcome number. And then everyone in A is like here. And everyone in B is like something like that. So it could be that the group means are here and the grand mean is like here. And then if everyone is really spread out, then if I imagine this all as one big group, it's going to be really like this person could just as easily have come from this group or just as easily have come from this group. And so we're going to get a really low p-value. The F statistic is going to be a small number. Whereas if I had exactly the same distribution, wrong word, if I had exactly the same arrangements of group means and grand mean, and everyone was really closely clumped around this one and this one and this one, then this person couldn't possibly have come from this group. They're way too far away from the grand mean, from the group mean. And so this one would have given me an F being big. Because the distance between the group means is way bigger than the distance between the individuals and their group mean. That's the idea of how the F statistic will respond to how close everything is to their group means. And then what you have to do is you need to look up, you need to know, that's the test statistic. And you go, well, what are all the test statistics that could have happened if indeed there is no difference between the actual distribution of the people in the different groups. So if actually, in reality, for all possible people that could be in these situations A, B, and C, which group you're in doesn't really make any difference to the result on average, then it really is just a big grand mean, and the fact that these are far apart is a coincidence. And we're going, well, if we had done all of the possible ways that people could possibly have ended up in these, gotten values in all of these groups, and we calculate all the possible F statistics that could possibly have been calculated, and we compare ours to that, it'll look like this. It looks like a chi-squared test to you, but the keeper of the distributions knows it's different. Like it looks like a chi-squared distribution. And I get my F statistic and I add up this probability here. And that's the p-value. But to tell the person who is, say the computer, to tell whoever's going to look up this p-value which F distribution you have, you need 2 degrees of freedom. So you have, so the distribution is F with some number and some number degrees of freedom. There will be 2 numbers, and those numbers are here. This number and this number. You need both of them to tell which F distribution you have. Chi-squared test, you only need 1 number. T-test, you only need 1 number. Z-test, you don't need any numbers. And the F-test, you need 2. And it comes out to a p-value, and you know what to do with a p-value. You see if it's low, and if it's small, then you reject, and if it's big, then you retain. And unfortunately, all of this answers one question, because the any hypothesis test is only capable of answering one yes or no question. And the one yes or no question that this answers was, are these means all equal? Or if you like, does being in a different category make a difference to the outcome? And so when I come down here and I get, for example, if my p-value came out as 0.35, I would say, I would retain. Do we use retain in this course? I would retain the null hypothesis and conclude all means are equal, i.e. the category makes no difference to the outcome. Well, the box and whisker plot will tell you, and you'll go, oh, well, you look at it. I mean, this is just as good as a box and whisker plot, and you can say, well, it doesn't look like the category makes a difference to the outcome. But the whole point of the chi-squared test, of any statistical test, is for it to give you a much more calculatory way to do it, that people will be more convinced by, rather than you just saying, well, I looked at the graph and it seemed obvious to me. Yeah. The problem is, this is the problem. If my p-value came out to 0.003, right, then I would reject H0 and conclude not all the means are equal. But it doesn't tell me which mean is different to which mean. All this test does is answer the one yes or no question of, are the means equal? And the answer is either yes, they're all equal, or no, they're not all equal, but it doesn't tell you which is different to which. So you have to follow it up with extra tests to compare the different categories to each other. So I go all the way back to the beginning and I go, right, what if I just had A and B? Oh, cool, there's only 2 categories now. I'll do a t-test, because that's what you do when there's only 2 categories. What about A and C, A and D? Cool, I'll do there's only 2 categories now. I'll do a t-test. And you do all those t-tests, only you don't. The computer does it all for you. And in fact, the computer doesn't really do a single t-test. It creates one standard error for the confidence intervals in the t-test that goes with all of them, and it spits some stuff out, and you get, like Chuki's honestly significant difference or something. Yeah. This is the sort of thing we can talk in more detail about at some other time. These are called pairwise tests of significance that I was talking about, where you look at two of the categories at a time. And what the computer will produce is something like this for every possible pair of categories. So this one had 1, 2, 3, 4, 5, 6, 7 categories. So there will be 7 choose 2 comparisons. My situation had 4, so there will be 6 comparisons. And it will give you a p-value to compare those situations to each other. And each of those comes from a t-test, but it says p adjusted because what they've done is they've bumped all, because you've done like a very large number of tests, there's chances of just accidentally finding differences that don't really matter. And so they bump the p-values up so that you're less likely to find a difference by accident. So I would look through all of those and I'd say, oh, a compact versus two-seater is, yeah, that's significant. Compact and minivan, yep. But there doesn't seem to be any difference between minivan and two-seater. And mostly what you do is you just look at the graph, which was here somewhere. Anyway, yeah. And ANOVA can be really confusing when you've gotten stuff at the end with the box plots, because this one's probably going to come out that blue is different to green. Blue is the same as green and green is the same as red, but blue is different to red because they're far enough apart from each other for the statistics to be able to perceive a difference between them, which can be really confusing. Yeah. I'm going to stop there. But before I stop properly, I'm going to ask one more time. Questions, thoughts? You're welcome. For future reference, I don't like being called Dave, but I'm okay with the thanks. I'm going to stop the recording now, if I can find it.